Thank you very much. And let me take the opportunity to also thank Yiannis for hosting this event, and Manuel. So as Andrew, which is going to speak in the afternoon, pointed out, so for the moment it was mathematics by large language models. And so now I'm going to try to do some mathematics for large language models. So basically the idea is that, what is the mathematical structure encoded in the data that you input into the large language model? Okay, so basically we define, so what the input to the data of a large language model is just sequences of symbols and probability of the next symbol. Okay, and it strikes me that this is a very, very nice mathematical object, which we use all the time in mathematics. Appears everywhere, and that thing, for example, you can see it immediately if you consider language as a poset, as a partially ordered set. So you can say that red is less than or equal to red rose because red is a subtext of red rose, and you can have so in this case you can consider all possible extensions. Maybe you can consider on the right and on the left. Some models do on the right and on the left. Some models do just only on one side. But basically, if you think of this poset, what you're actually doing is you're considering the filter the upper set generated by red, right? So all the expressions that contain red is basically just from the poset point of view is the filter generated by this element. And the other way around, if you take all the text included in some text, this is the lower set. It's an ideal. So this is like one of the most basic things in mathematics. And when we have a poset and we have the set of ideals or the set of filters, this is a kind of completion into a lattice, and the original set lives in there. But it has nicer properties. Like for example, it has logic, okay, because it has a Boolean structure. So this is. This is what I was saying about lower sets and upper sets. Even if you consider, so usually people don't consider language as a poset. Most often people consider it as a monoid. So you just take these two texts and you just put them together and you create a new one. And if this new one is correct, then you accept it in the language. If it's not correct, you sort of put 0. But of course, to go from the monoid to the poset is a kind of very easy task. So the monoid will define for you the poset. And if someone wants to know exactly how, I can explain. I mean, it just has to do with sort of thinking of the monoid as a category with one object, and the text being the arrows of the category, and then constructing another category, which is called the factorization category. And you can immediately construct this poset from the monoid. Now, why use the poset idea? So let me just say that this is a very old idea in semantics and linguistics, that distributional semantics means that, if you want to know something about the meaning of things, you should know something about the context in which they are used. And so if they're used in similar contexts, then they may have similar meanings. That's the idea. So the mathematical version of that, I would say, distributional semantics says that the ideals or the filters of a language poset or a language monoid say something about semantics, about the meaning. Okay, so I want to sort of study this structure, and the study of ideals, of course, is a very well-known subject also for commutative algebras. In the case of commutative algebras, this is a sort of very well-known duality between ideals. If you take an algebra, like for example, polynomials of two variables, and if you take all prime ideals, then they basically make C2. So this is the construction of a spec, and you can go from the algebra to the geometric object, which is the complex plane. And there is an equivalence between the two, which is sort of the foundation of algebraic geometry. So this idea of taking ideals of an algebraic object and constructing something which is sort of dual to it, it's a very well-known idea, very old. And so I'm going to try and implement this in this particular case and see what this means for our case. And so the idea is that can we generalize all these constructions that hold for posets or monoids or algebras, commutative algebras, of course. That was a commutative algebra that I talked about, the polynomials and two variables. Can we generalize them to text extensions with probabilities? Okay. So the question is, do they define some mathematical structure? And what is the mathematical structure if they define? And so what I'm going to talk about is exactly that. Okay, so this current talk is a joint work with Stéphane Gobert. This paper was also uploaded, not because of the NeurIPS deadline, but it was also uploaded just a couple of days before on the on the archive. A previous work on that. So this paper is directed metric structures arising in large language models, yeah. And the previous work was with Ty Donai Bradley and John Tarilla, and that was written completely in the setting of enriched categories, because enriched categories is the natural algebraic setting in which this lives. But in this paper, in the new paper where we sort of continued the project, we decided to use basically tropical geometry and directed metric spaces, but everything has an equivalent description in category theory. So what I'm going to try and do is I'm going to try and say everything in metric spaces and tropical geometry, and at the same time sort of point out what are the categorical explanations of things and the categorical interpretations. And there were some experiments done by this group of Liu, Trager, Achille, Pereira, Zancato, Stefano Soato, where they use this kind of, what we're going to see is called the Yoneda embedding, basically. And they perform semantic tasks, because this is supposed to be about the semantic information. And this is the paper, and they had very good results, actually, using this kind of semantic vectors, which I will describe. So first so this is the content. So the idea is that basically we go from probabilities of text to distances. Okay, so we convert from probabilities to distances, and that's kind of an accident, basically. We could have done everything in probabilities, but because people didn't develop that theory in probability framework, but they developed it in the metric space framework, we work with metric spaces. Then we're going to see how we can construct basically what I was talking about before about lower sets and upper sets. We can construct an isometric embedding of this text metric space into some polyhedron. And we'll see that the texts are actually in this polyhedron are mapped to extremal arrays. So they're very special elements of this polyhedron. And then we're going to see that this polyhedron can actually be described as a min plus a tropical linear space, or tropical module, if you want. This min plus spanned by some vectors. We're going to see the equation satisfied by the text vectors. And then there's some duality. So basically, this is supposed to be a sort of space of meanings, but the texts are only at the extremal arrays. Okay, so that's interesting, because the texts are, it's like some sort of, maybe you can think of, you have observable variables and hidden variables. And the observable variables are these extremal arrays, and the hidden variables are everything else. But what becomes apparent is that there's a duality between considering extensions of text and considering restrictions of text, which a priori, it's not clear that you would expect. But if you basically bound the whole corpus, then there's this kind of duality I'm going to talk about. And then there's something called the Isbell completion, and maybe I'll mention that. Probably we won't have time. But and then some directions of future research and some speculations with respect to something called Morita equivalence, and could be sort of an equivalence between different languages because they have the same semantics, or to the extent that they have the same semantics. So basically, let me first describe what I'm going to call a probabilistic language model. So this is just a triple, a set which contains some texts. This is the subtext order, and we have some function with values in 0, 1. And the basic thing is that if text AI is contained in text AJ is contained in text AK, the probability to go from AI to AJ times to go from AJ to AK is equal to the probability to go from AI to AK. So this is a standard property of conditional probabilities, okay? And because transformers work this way, it makes sense to consider this structure, because the way you introduce a text, and then you use the probability of all possible next words, you pick the most probable one, and you put it in your text, and you keep doing that, so the probabilities multiply. And so basically this is the main property. And immediately let me say something. So we want to understand what is this thing, okay? So basically this is, you can think of, you have this poset, but you're also adding these probabilities now, and the probabilities express themselves within this law. So now let me immediately talk about what's a directed metric space. So the directed metric space is basically the minimum. It actually turns out to be very natural from the categorical point of view, but the minimum thing you can ask for in a metric space is the triangle inequality. So it satisfies the triangular inequality, and the distance of something to itself is 0, but it doesn't. But the values are in minus infinity, infinity. You know, if delta AB is equal to 0, it doesn't mean that A equals B, for example. And of course, delta AB is not equal to delta BA, so it's non-symmetric. That's what makes it directed. So, the first thing we notice is that given this probabilistic language model, we can immediately define a directed metric space. And the way to do that is to just take the distance to be the minus log probability if AI is less than or equal to AJ, and to put infinity if AI and AJ are not comparable. Okay, so and then you can check immediately that this satisfies the triangular inequality. Okay, and satisfies the triangular inequality in a slightly degenerate way, but still enough. So basically, when AI is less than or equal to AJ, less than or equal to AK, then the inequality becomes an equality, and in any other case, one of the two sides has to be infinite. Okay, so it does satisfy this sort of inequality. And the first thing to notice is that the metric defines the poset. If you know the metric, then you know the poset. Because you know, if you have three elements that satisfy the metric, the triangular inequality is an equality, and you know that one of the distances is the AI to AK distance is finite, then you can tell that AI is less than AJ, less than AK. And categorically, for those of you who are familiar with category theory, this directed metric space is exactly a category enriched over the monoidal closed category minus infinity, infinity, considered as a poset. So you consider it as a poset with the opposite of the usual order, and with monoidal structure given by addition. And why is that the case? What is the point of a triangular inequality? The point of a triangular inequality is just the composition of morphisms. So if you write down the composition of morphisms, you get precisely the triangular inequality. Okay, and that's not new. This was discovered by Laver back in the 70s. He discovered that that metric spaces were actually categories, or enriched categories in that sense. This is a kind of interesting story, because it makes everything canonical afterwards. Because when you have a category, there's a machine, you can crack the machine, and you can, you know, get nice definitions, which is important. So the first thing to do is to define this basically, well, this P of L, you should think of it as a generalization of the space of ideals, or the space of filters. Okay, just like when you have a poset, you could consider filters or ideals, and they give you a lattice. It's something analogous, okay, but it's much more rich, because now we have numbers. So what is the definition? The definition is exactly that. The definition is, oh, let me see if I can use this. Oh yeah, there you go. Yeah, so you take basically elements in minus infinity, infinity included, and you have this sort of very suspicious looking inequality, which looks like a triangular inequality, and then we'll see it's a triangular inequality actually. So xi less than or equal to xj plus dij, and you have the transpose matrix defines for you p hat. And there's a metric called a func directed metric on this space, which is just the maximum of the differences for xi different than infinity, and not all of them can be infinity. We've taken this out. So, you know, so the first thing to show is that basically these are the elements of P of L. It's not just an arbitrary definition. These are precisely, from a metric point of view, they're non-expansive maps. So if you put this func metric on minus infinity, infinity, if you put this metric on minus infinity, infinity, t minus s basically, then you can check that this is the space of non-expansive maps. So, you know, basically contractions are equal, or isometries. And categorically, this is the category of presheaves, and p hat of L is the category of co-presheaves for the space. Now remember, like if you have presheaves, what are presheaves? It's just a functor from your category into the enriching category. The enriching category in minus infinity, infinity, the category is L. So you have, and you know, if you check out what the condition has to be for this to be a functor, you get precisely this. So you can, so metrically is this space of non-expansive maps, categorically is the category of presheaves. And so now the first thing you do when you have this story is you do the Yoneda embedding, because you can embed in your initial category into this category of presheaves, or from a metric point of view, you can embed your finite metric space into this polyhedron. And the Yoneda embedding turns out to say that this is an isometric embedding. Okay, so with respect to this distance. And by the way, let me give out something else also. This distance, capital D, that we defined, it also has a categorical meaning. It's actually the home on the presheaves. So this is the home on the presheaves. Because the presheaves is also a category over minus infinity, infinity. The presheaves category inherits the same structure as the original category. So you have, so basically this turns out to be an isometric embedding, okay? And you have the unit embedding and the co-unit embedding into the dual polyhedron. Okay, so, yeah, and now you have something called the unit lemma, which everybody knows in category theory. And it tells you if you have a home, so if you have the home from a representable functor to any functor, then then this is equal to, so you have basically the representable functor is so d dash ai is the function. Okay, yeah. So let me go back for a second. So I want to make sure something is clear. So the map is precisely you send ak to the distance to ak. Okay, this is the map. And the other map, this is on the unit embedding, and the co-unit embedding is you take, so basically the first one you take restrictions, and the second one you take extensions. Okay. Then the unit embedding says that, you know, xi, which is x of ai, is the distance from this d dash ai to x. This is precisely the unit lemma, but in the metric framework. And now we see that the defining inequalities of this polyhedron do have also a metric interpretation. And the metric interpretation is that because xi is the distance from, you know, y of ai is precisely this unit embedding into x, and we see that this inequality, xi less than or equal to xj plus dij, is precisely actually the metric inequality for this metric d and for this images of the unit embedding y of ai. Okay, so what does that mean? It's kind of like a metric span, basically. You can think of, you know, you have this initial vectors. You just think of them as vectors. Y of ai are vectors. Their components is minus log probability of extension over or of restriction. Okay, and now you define. Now you want to look at all other maps x that, with respect to this element, to these points, and with respect to this distance, satisfy a triangle inequality. Okay, so it's a kind of metric span in a sense, but it's convex. Okay, so it's not the smallest span you can make. You can make another one which is smaller, which is not convex though. So these are triangle inequalities for this map. Yeah, and we have the same thing for p hat of L. So remember, p of L is for restrictions and p hat of L is for extensions. So now we have the spaces, and I think these spaces are kind of a natural place where you find vectors, basically, because when you do language models, you know, people use always vectors. But why use vectors? You know, where could you find these vectors arbitrarily? And here we have a place where these vectors are actually precisely the presheaves. And it's not anything specifically you know, complicated. It's just the vector of probabilities of extension. But then when you take the other points of this space, you get all these other vectors, which you don't know what they are in terms of the probabilities of the original ones, but they're there. So it would be natural to expect to get a sort of vector model of language. Okay. So now we have this P of L. We went there because metric theory is much more well understood than, you know, probabilities in that sense. But actually, if you go back to the probabilistic picture, it makes it's actually easier to imagine, at least for those which are not, you know, steeped into tropical geometry. So if you basically, so we went from the probabilities by taking minus log, we went to this P of L. Now, if we want to go back, we just have to take e to the minus x. Okay, just the inverse map. And what we find, this Q of L is the image of P of L by this e to the minus x map. And what we find is precisely this equality here. Okay, so these are defined by a very simple inequality, zi greater than or equal to the probability of aj given ai times zj. First thing we notice is that this is a polyhedral cone. Okay, This is a cone because if you scale both sides by lambda, it doesn't change the equation. So, you know, the whole ray is in there if a point is in there. Second thing is, of course, that this is actually a generalization of something which is a well-known object, which is the Stanley's order polytope. So Stanley defined a polytope associated to any poset. And if you put the values 0 or 1 only for the probabilities, then you recover that construction of Stanley up to the fact that Stanley does not take the full ray. It doesn't make it a cone, but it takes a box. So it takes intersection, has the variables between 0 and 1. And also notice that now we're in 0 infinity, right? So this minus infinity infinity, if it makes you feel strange, because, you know, what are these metrics that take negative values? Well, secretly, in any case, we're actually, when we take this, the negative values happen because we take in this minus log. But in reality, we're working in the positive cone. So this is a polyhedral cone inside the positive orthant. And the fact that we took away the infinity, infinity, infinity vector just means that we took away the origin of the cone. Okay. All right. So, and then, of course, you can define the func metric defines a metric on this polyhedral cone. So this is actually a directed metric cone also. And if you just directly apply the map minus log, you will get that this is the metric on this polyhedral cone. So originally we said that L is isometrically embedded into this PL, but now we can say that L is isometrically embedded into this QL because, you know, we just have to exponentiate the map from PL to QL, and we get this. This is the metric. So it's also an isometry. And in fact, actually, the two metrics are very simply related by logarithm and exponential. Okay, this kind of, I mean, I'm not an expert in this story, but this is related to Hilbert's metric. So it's a kind of classical metric. It's a directed, non-symmetric version of that. Okay, so yeah, so this is the same thing for Q hat. And we have this isometric embeddings, as I said before. Okay. Now, so now we come to the part that I was talking about, that we have our original. Oh, and by the way, notice something interesting, that in general, if you have a finite metric space, you cannot embed it in some Euclidean space with some Euclidean norm isometrically. Okay, that's a sort of very hard constraint. It has to be satisfied. But here, because we're using this, you know, natural category theoretic construction, we get an isometric embedding using this func metric, this maximum metric. So no information is lost, okay, from one to the other. Okay, so now the next thing to check is that, to show is that actually how does it sit in this polyhedral cone? And the theorem says that actually it sits as an extremal ray. And so now I want to make clear what I mean by extremal ray. Q of L is a cone, so everybody knows what extremal rays are. It's a ray that cannot be written as a positive linear combination of non-proportional vectors. Okay, so you cannot write it as a positive linear combination. So we know this is a ray in a polyhedral cone, and when we map by minus logarithm to P of L, the image of that is an additive ray. And why do I call it additive? Because a ray is invariant under scaling, so multiplication by lambda. If I take minus log, it becomes addition. So then it becomes invariant under addition by minus log lambda. So we may call it an additive extremal ray, but we're just going to call it an extremal ray. Okay. So basically the theorem says that that the Yoneda embedding, the map that maps AK to the function y of AK, which is the distance from everything to AK, it generates an extremal ray. And there's an analog for the map from the co-Yoneda embedding, which is the extensions of AK. And the basic reason is very simple, has to do with the fact that if you have AI less than or equal to AJ less than or equal to AK, then this inequality becomes an equality. And so what this means is that the corresponding Yoneda vector satisfies the defining equation of the polyhedron as an equality. Okay, so if you have enough of those, you get an extremal array. Okay, yeah, and to show you a little bit about how this works, this is an interesting point here. So normally, if you have this poset of language, you might as well add a global minimum element, which is sort of the empty text. Now, when you have numbers associated to it with these conditional probabilities, it becomes much less trivial to add the empty text. Because if you add the empty text, you have, anytime you have AI less than or equal to AJ, if you have like red less than or equal to red rows, you also have the empty text. So that means that the probability from red to red rows is the ratio of the probability for red rows divided by the probability for red. So in other words, instead of having just conditional probabilities, now you know that the conditional probabilities all come from a global probability distribution. Okay, but I have to say that the people I spoke to, well, these people in Amazon that did these experiments, explained to me that this is actually is perfectly reasonable assumption to assume that A0 exists. If A0 exists, it simplifies life very much. For example, you know, the one thing you can see immediately is that the equation that we have, which is this one here, if AJ, probability of AJ given AI is the ratio of two probabilities, then you can define new variables, and you know, y tilde is the probability of AI given A0 times yi, and then the equation becomes just this. So this is so this simplifies life, and then you can show, but you can actually prove we can actually prove the theorem without this assumption, but it's very easy to see if you have this assumption. And so what we show is that actually in these new variables, a generator of this extreme array is a positive scalar multiple of the characteristic function of the lower set. Okay, so basically what it says is that, okay, so maybe I should specify one thing. So as I said, all initial texts go as extreme arrays. But there are many more, exponentially more extreme arrays actually than the original texts. So the question is, where are these other extreme arrays? And initially, I thought maybe there are other texts. But what we ended up showing is that they're not single texts. They are collections of texts. Because what they do is they correspond to lower sets. So you get basically the lower set completion on these vertices, on these extreme arrays. And only the principal ones correspond to texts, and the other ones are collections of texts. Okay, and there are such collections of texts such that the diagram, the Hasse diagram of the corresponding lower set has to be connected. But of course, if we have this A0 element, then they're always connected because they're connected through this lowest element. So again, the picture is that we have this polyhedral cone. There's special extreme arrays that correspond to principal lower sets that correspond to texts. And there are other extreme arrays which correspond to other lower sets which are not principal. So that means they have more than one generator that generated by these elements. Okay, and then there's a dual result where instead of having, for the polyhedron Q hat of L, instead of having lower sets, you have upper sets. Okay. Yeah. All right, so now that we understand this structure, okay, well, that's the first level of understanding. The second level of understanding is that actually this is very much connected with tropical geometry. So I remind you that the min plus semifield is defined where you take minus infinity, infinity closed, and you consider these operations minimum and addition as opposed to addition and multiplication, and you should think of this as log algebra. Okay, so it's logarithmic, and of course the logarithm of the product is the sum of the logarithms, so that makes complete sense. But what about the logarithm of the sum, which is not very nicely behaved? Well, actually, you can make it nicely behave because you have this famous identity. It's a very nice identity here. It tells you that if the logarithm of the sum under right scaling becomes the minimum of the two numbers. Okay, so this temperature parameter is the temperature parameter that appears also in you know, in the transformers and all these models. And so basically it tells you that you can do that, and also it tells you that you can go the other way around. Whenever you have a linear equation in min-plus algebra, you can transform it into a Boltzmann-weighted linear combination in the usual algebra, because you can just run this thing backwards for small t. Okay. All right. So first, let me notice that the fact that D is a directed metric space, what does it mean? So you have the triangle inequality. Well, the triangle inequality says that dik is less than or equal to dij plus djk. It's actually the minimum of dij plus djk. Okay. But this now, if you look at it from the point of view of the min-plus algebra, precisely says that d squared is d. So it just says that d is a projector. So this is not important, basically. Okay. So that's the first thing to notice. Now you can check immediately that the fixed part of this idempotent dx equals x. If you look here, if you write down this equation, dx equals x means that, you know, xi is the minimum of dij plus xj, which is precisely the equation, defining equation for P of L. Xi less than or equal to xj plus dij. So the defining equation for P of L is precisely written as dx equals x. Okay, so P of L is the fixed part of this projector. And because it's a projector, this is also the image. So because it's the image, we can see immediately that this is basically the min-plus span of the column vectors of D, of the matrix D. Okay, so this is the min-plus span of the column vectors of the matrix D. So this P of L, this polyhedron, is really a linear space in a sense, right? It's linear space not in the usual arithmetic, but in the min-plus arithmetic. Now, and then that means that we can write, immediately what it means is that we can write any element, as I was saying before, as a linear combination of the column vectors. So x is sum of xj d dash aj. So we can get an expression of this kind of mysterious points of the bulk points of P of L. And they are just linear combinations, min-plus linear combinations of this vectors corresponding to texts, basically. So they're min-plus linear combinations of texts with some coefficients. Okay, and the same thing happens for p hat. P hat is the image of the transpose matrix. So in other words, p hat is just the row, the min-plus row span. So one is the column span, the min-plus column span, and the other one is the min-plus row span. Okay, actually, you know, so the fact that actually P of L is the min-plus span of these vectors categorically is to be expected in a way, because this mean actually is a colimit. So what it means is that you can write any presheaf as a colimit of representable presheaves, okay, which is something you expect. And the same thing happens for these copresheaves. They generate via colimits presheaves. And we will see though that the min, if you take if you take the max plus algebra, this corresponds to limits, and it does not generate all of the presheaves, so you cannot write them all as max plus sums. Okay. So now we can write down equations, for example, for these vectors. And the fact, you can read the equations precisely from the fact that d squared is equal to d. So the fact that d squared is equal to d implies the equations that the Yoneda embedding of text ak is the sum over all texts that are contained in ak of the Yoneda embeddings of these texts times this coefficient. Okay, so it's a kind of, you write a text as a linear sum of all the subtexts with the corresponding coefficients. Okay, and the same thing you do for D transpose and then you get another equation for the counted embedding, which means you write this counted embedding as the sum, this contains all these probabilities of extension. You write it as a sum of probabilities of extension of all the texts that contain it. You see here AJ is greater than AI, and here AI is less than AK. So there's the dual situation. Usually in large language models, we always think about extensions, but this seems to say that actually we could consider dually just restrictions and get similar results. And then in one way, we can consider that the neural net, when it's learning all this stuff, it's finding solutions to the system of equation, basically. Okay. So we can also, as a byproduct of all this analysis, you can also show that you can write down explicit coordinates for the other extremal rays, which are not principal extremal rays, and they come in this flavor. Okay, so they're not. So basically, it depends on if you have a lower set which is generated by some texts. I don't know, red, green, I like coffee, whatever. Generate some lower set. Then you can write generator for the corresponding extremal ray as this min plus sum. Okay, and just to give you this whole picture here, because we said this is a kind of linear space, P of L. It turns out that this distance actually behaves as an inner product. It's linear and antilinear in both of these variables. Okay, so you don't just have a linear space; you have a linear space with an inner product. Okay, and when I say antilinear means that not only when you have a a scalar lambda 1, it comes out as minus lambda 1, but also the mean structure goes to the max structure. Okay. All right. So I mentioned something about a duality between extensions and restrictions. And the duality actually is a general property of, it's a general thing between dualities that have to do with tropical matrices. In this particular case, because our matrix is an idempotent, it turns out to be very simple and very nice to see. Because all it means is the following simple thing. So we have this equation that defines the elements of P of L, xi less than or equal to dij plus xj. And when we see that if we take xj and xi to the opposite sides, we get minus xj less than or equal to dij minus xi. So this means that dx equals x if and only if the transpose of minus x is equal to minus x. So if only we could, of course, what the immediate problem that one sees is that if your variable is in minus infinity, infinity, where minus infinity is not included, then it's not going to preserve this set, this minus operation. But that's why we complete the min plus semi-ring, and we consider minus infinity, infinity, and you can complete it, and in a very completely consistent way. And the consistent way, basically, what it means is that you have to say that the plus infinity remains an absorbing element. Like 5 plus infinity is infinity, but now we have to say also that minus infinity plus infinity is infinity. Okay. All right. So if we do that, then we have these two inverse maps from P of L to P hat of L, which is just sending x to minus x, and vice versa from P hat of L to... So basically these maps go from the column span to the row span. Okay. And you can check that they form an adjunction in a categorical theoretic sense. And this adjunction, basically what it means is that d of ax comma y is the transpose of x comma by, and then you can check that this immediately you can see it means that d of minus x comma y is d of minus y comma x, and you can check this by hand. It's true. So you get this adjunction, and that means that you can write down these two maps are isometries, give you isometries between P of L and P hat of L. And also the maps are antilinear. Of course, antilinear means that it changes min to max. This map may look somehow trivial because it's just x to minus x, but it looks much more interesting if you go to the exponential side. Because in the exponential variables, it just basically is inversion. The same story holds for Q of L. And then in that case, zi goes to 1 over zi. So there's a symmetry. Okay, and so let me try to show an example of this. Oh, yeah, and we can write down this is also in coordinates. So before I said that if I have a vector corresponding to some text, I can write it down as a sum, as a linear combination of all the text it contains. And you can apply this on the level of this duality. And you can see that while you started with d dash aj, so these are texts that are contained in aj, you end up with d aj comma dash, which is texts that contain aj. And the same thing also in the other way around. So this minus x, and this is to be expected, of course, because all this means is that you go from columns to rows. You go from the column span to the row span. Okay. Yeah. So it would be interesting to try to find some sort of experiment to see what this means in practice. But for a very, very small scale experiment, you can see this. So let's say you have just your corpus is made out of 3 texts: red, color, and red color. Okay. Then this is the matrix. What does it mean? It means that the distance from, remember that this actually maybe it's easier to see the probability first. So the probability to go from R to R is 1, from R to C is 0, and from R to RC, let's say, is 1/2, and so on. Okay. So you get this matrix, and if you take minus log, you get this matrix. So this is a metric. This is a very simple example of the metric that we're kind of talking about. And for this, we can compute several things. First, we said that, well, let me show you a picture first. Actually, the picture is always first. Sorry. So how can you show a picture of this? To show a picture of this, you have to take a section of this polyhedral cone with a simplex, with a unit simplex. And then when you get the section with a unit simplex, you're going to get some polyhedron, okay? And the extreme arrays are going to produce basically vertices. So you expect to see all these lower set appear as vertices. And in particular, some of them are going to be the original texts. So this Q0 is precisely this intersection of Q with delta. Okay. And here it is. So you see that on the left, the cross section, this is the Q, so this is Q tilde. This corresponds to upper sets, and this corresponds to lower sets. And you can see that basically, but you remember you have to take connected upper sets and connected lower sets. So here, what is it? There are 3 principal ones. There are one generated by red. Okay, the upper set generated by red, it just contains R and RC. The one generated by C, the one generated by RC, and then this one here is the one generated by R comma C. Okay, so this is the lower set generated by 2 different texts. It's not a principal one. On the other hand, here you only have 3 vertices because the one generated by R and C, the lower set generated by R and C, is not connected. So it doesn't appear here because it's all the connected ones. Okay, so now let me go back to the, yeah, so this is basically just what I said. Okay, this is what I said now. Okay, so this is how it looks. Now, another thing you may do is you may want to approximate. Remember, we had this matrix where wherever these m's are, there was infinity. So a natural thing may be to just approximate this infinity by some big number m. So you can do that. And then if you do that, you can also draw this Q of L's and P of L's. And then you see that, you see on the left, you actually get, you see now that the number of vertices is equal. Okay, because when you have a finite matrix, the number of vertices is preserved under this map, x goes to minus x. But as m goes to infinity, you're going to get the previous picture where this actually is going to collapse. R and RC are going to go on the boundary here. This is going to go on the boundary and it's going to collapse. So this vertex and this vertex are going to disappear, but this vertex is going to survive. And here, so here all the 3 vertices are going to disappear and just the 3 will survive. So this is the kind of structure that the data has basically. Okay, the data has this kind of polyhedral structure, and different languages will have different polyhedra actually, and this kind of duality, right? So basically, if you think about this P of L and P hat of L, you're supposed to think of it. I mean, the way to think of it is a semantic space, because it's not enough to know just the vector corresponding to a particular text. You have to know the distances between texts. So you need the whole space basically. So it becomes a sort of. So the thing is that it's not really just by any means a list of numbers. It's some sort of structure that's been learned, and that structure could look like that. So one thing that we kind of thought to check about is because you see when you have a corpus, of course you always want to add more corpus. So this construction should behave nicely under extending the corpus, and it actually behaves very nice. So the way it behaves is that if you have an L1 initial corpus with D1, and if you just get another one which is isometrically embedded in the first one, which means that you don't want to screw up the initial probabilities. You want to keep these as they are and add some more. So that means that there's an isometric embedding. Then there's an isometric embedding of the corresponding polyhedra that respects, that is compatible with this inclusion. And what's more, the image of the small polyhedron inside the big one is a retraction by a non-expansive projection. Okay, so what does it mean in retraction? It's the image by non-expansive projection. The fact it's non-expansive means that it's not going to blow up your distances, so you can use it to estimate things. And it's a projection, and you can write down this projection. And now immediately you see, so this is a kind of standard formula. You can kind of sense that this could be what's needed, because when you have a projection, you have sum of vi tensor vi star. So this is kind of like a tropical equivalent of that. But you can compute everything by hand, and immediately one thing you can do is you can consider the very kind of stupid language model which just has the words. And they're not comparable to anything else, just the words. But they're just in there. Okay, so you can then write down what the projection is going to be for the words. And what you get is that you get this formula here, that it's going to be a linear. So you get that any text now, in other words, you project the whole big space into the space generated by the texts. And then you get this projection formula, which is basically sort of linear combination of the unit embeddings of the word vectors weighted by some probability. And now you can go one step further and apply what I was saying before, that whenever you have a linear equation in min plus algebra, you can always raise temperature a little bit and get a Boltzmann weighted linear combination of actual vectors. So this would say that if we play this game, and then for small t, we get that the exponential of this projection vector of the text is a Boltzmann weighted linear combination of the vectors for the words, which somehow to me reminds me of what happens in the attention layer, where you write down, you have a vector and you write it as a Boltzmann weighted linear combination of word vectors. Okay, so okay, I don't have much time, so let me just say a word about this. So basically, as I said before, we took co-limits, and any pre-sheaf can be written as co-limit of representable sheaves, and therefore we got the nice result that P of L is actually generated as a mean plus span of this unit embedding vectors. But now, if you take limits, you get something interesting, but maybe kind of too interesting because it's a little bit hard actually. So you don't get everything. You don't get the whole polyhedron, but you get something which is a polyhedral cell complex. So in other words, what am I talking about? I'm talking about the image of D max. So before we had the image of D min, but we can define the max operation. And of course, the difference between D max and D min is that D max is not a projector anymore. It doesn't square it to itself. It's not an idempotent, okay? So it doesn't have this nice behavior. But of course, you can write down an adjunction with respect to this guy here. And you can compute what these fixed points of the adjunctions are. And you get something which is called the Isbell completion. So maybe you've seen this in category theory. It's a sort of duality between sheaves and pre-sheaves. It's called the Isbell adjunction. In the case, so we've been working with the minus infinity infinity coefficients that we like. But so there's a theorem by Willerton that if you work with zero infinity coefficients instead of minus infinity coefficients, then you get, with this construction, you get something called a directed tight span. So the tight span is sort of basically, if you have a finite metric space, it's kind of like the smallest, it's an injective object in the category of metric spaces that you can map your metric space into. It's kind of the smallest metric space that you can map it into isometrically. But the problem is that it's a polyhedral set complex and it's very far from being convex. People use that in phylogenetics, actually, to find the distances, because then you have the alphabet in 4 letters and you have the genome and so on, and you can do that. But I think it's interesting, but it's much less useful, I think, because it's not convex. Basically, that's the problem. But we have a theorem which says that the lattice closure of this isabel completion is precisely P of L. Okay, so it lives in there, and if you complete it with respect to mean, then you get it back. Okay, so I should be wrapping up. Yeah. Limit, yeah, so this is what I said. So, okay, so we have this overall picture of our initial metric space, and basically we take all these possible extensions, and we said this is a nice object which appears in many places, like, in the completion by upper sets of posets, appears in the ideals of monoids. The ideals appear also in the category, in the construction of spec, which is a duality between algebra and geometry. And what is the corresponding idea here? Okay, so we did that. Okay, yeah. So if we think that this P of L somehow encodes the meaning, the semantics of the language, then the natural thing to consider is that if you have 2 different languages, they should have in some way isomorphic such P of Ls. But of course, the question is, in what sense isomorphic? I mean, so basically, the natural thing that category theory tells you to do is to consider the notion of Morita equivalence. So in other words, if you have 2 categories and you have their pre-sheaf categories being equivalent, that basically means that you have that means that you have a Morita. It's called a Morita equivalence, and this is a very standard notion and useful in mathematics. And so the expectation would be that these 2 different polyhedra would be Morita equivalent. And then if you wanted to find something, and why do we assume that they have there should be some isomorphism between the polyhedra? Basically because of translation, okay? So because we can translate between languages. I mean, it's not exact, but to some appropriate approximation. So now if you assume that this is a Morita equivalence, or if you assume that this probabilistic language categories, these probabilistic language models, these directed metric spaces are somehow equivalent, then you may want to find invariance. Okay, so the fact that they are equivalent means that there may be some invariance. And this is a well-known notion in the study of Morita equivalence and so on. And the invariance is basically something called Hochschild cohomology. Okay, and the question is, what is the Hochschild cohomology in this particular sense? And so basically this would be, I mean, definitely, you don't have, it's not clear how to go from one sentence to another, but the question is, how can you go from the meaning of one sentence to the meaning of the other sentence? If 2 things have the same meaning. And the question of what is the Hochschild cohomology is actually not extremely clear, but there are some cohomology theories. In particular, there is one cohomology theory called magnitude homology, which kind of generalizes, which seems to be the right one. But then one would have to compute it and understand somehow what these invariants mean. So, okay, on that note, I think I'm going to stop here. Thank you.
Any questions?
Yeah, I had one. You're looking at text here, and you're looking at the properties of text.
Yeah.
Now, the way they are used in language model is that you have the text and then you convert them into continuous representation, into high-dimensional continuous representation.
Right.
Do you think this could be applied as a theory of the representation learned by language model, trained on text or other kind of sequential data?
Yeah, I think basically these vectors would be somehow correspond to these vectors that appear in the language models. The question is, why would there be any vectors? I mean, the natural thing for vectors, the natural notion of a vector, of course, is just the vector of all probabilities of extensions. If you had that, then you would be very happy. But and by the way, this is a huge dimensional model, right? So this is whatever the number is. So if you have like an n length text, this is of the order of n squared approximately. So if you had like a billion word text, it would be billion squared. So it's huge, right? So the question is, how do you then make an effective representation? So what I would imagine is that basically the neural network, of course, which is absolutely necessary because you wouldn't be able to calculate otherwise, is finding some sort of effective representations of these vectors to represent the word vectors and the text vectors. And one of the reasons why I think this may be true is precisely because of this one formula where we showed that this projection of the text vector on the space of words was precisely a sort of Boltzmann linear combination, Boltzmann weighted linear combination of vectors. So that looks to me like what one gets in attention module.
Yeah.
So I have a question that has been partially answered in the one, but so you think that there's probably a map between kind of a map between the embedding and PFL?
Yeah.
And in this case, because I remember that before we had this large language model, there was some result, in particular the result of conditional, where there was a similar idea saying that for two languages, the representation should more or less align with the transformation with small number of parameters. Do you think that will still be
here? Yeah, I think so, yeah. I mean, in a way, if we want a theory, I mean, the question is like, we want a theory of semantics, a theory of meaning, right? There should be some invariants. And in a way, we know where the invariants are located, because when you have a transformer who's translating from English to French, somewhere in the middle is a common representation, right? That common representation, if you can find the structure of this common representation space, so what I'm saying, the structure of this common representation space could be related to this, basically, because it's canonically constructed by, yeah. Sorry, yeah.
How do you encode the meaning in your model? And
of the what?
In your model, how do you encode the meaning?
Oh, the meaning.
And in languages, I mean, maybe it's not a story of invariant, but a story of lot of meaning and productivity.
Yeah, that's. I mean, you know, that's something that's learned also, but. The way you encode the meaning is basically by these distances, and let me.
It will be human that train.
No. The distances are just given by the probabilities. You see, the probabilities give you the distances, right? So it's just the probabilities. But yeah. So another thing I want to point out, thank you for reminding me this, is that this P of L has the structure, has also a Hating algebra structure. So it has a Hating algebra is a generalization of a Boolean algebra where you don't have a double dual to be equal to the original. And because of this min-max structure, you do get this Hating algebra. And actually, there's another structure, which is the internal home of the pre-sheaf. So the pre-sheaf category is better than the original category. It has something which is called internal home. The internal home is basically an implication operation. Okay, so this implication operation but this implication operation is a function. So something implies something else given a third thing. Okay. So this implication operation, actually something like that is what people, well, I encourage you to look at the results of, you know, the group of Stefano Soato and Matthew Trager at Amazon, because what they did is they precisely computed they did semantic tests. Okay, and they also did basically implication tests and so on. And apparently the results were very good.
And you have the duality between restrictions and extensions, yeah. And I think there is some nice things to do with this duality. On,
yeah, I mean, yeah.
Translation, style analysis, etc.
Yeah, I mean, I haven't really completely thought it through, but this duality, it kind of like explains some mysteries, right? Because if you say that it's the vector of restrictions of a text that should contain some information, if you have a word, this is just supported in one place, right? But if you look at the dual precisely has to do with all the extensions. Now, it would be very nice to have an experiment that kind of showcases this duality, and even better, an experiment that kind of uses this. So, you know, maybe the hope would be that somehow instead of training your model on the extensions, you can train it somehow on the restrictions and it would be smaller. I don't know.
I think it's one of the strengths of your model.
Yeah, maybe.
It's, yeah, something to think about.
I may make a comment that there's on the last question, then my own question. So there are these famous, the actual embeddings that language models produce. There was this famous observation of Mikolov and others that they satisfy simple linear relations, like the embedding of king minus man plus woman is very close to the embedding for queen. And then one can argue for these. One can understand it exactly by this model of the embedding vectors being derived from the relative probabilities of completion. So that's an example of where meaning comes out of these probabilities very explicitly. But then my question is that, of course, this is a huge dimensional space. This kind of universal embedding, and the actual language models, even the biggest ones, the embedding spaces are like 10,000 dimensional. And so the question is there a theory of embedding with distortion into lower dimensional spaces like there is for metrics?
That's kind of to be constructed, but I can imagine a natural way to do that. So what is a category? It's just basically like a matrix, right? Because you have like X, let's say if you have a category X, you have X cross X into whatever the enriching category is. But now you could imagine introducing intermediate steps. Like, you have, X cross M1, cross M2, cross M3, cross M4, and so on. So you can kind of compose them as bimodules, perhaps.
Well, you don't need that in this. So there's like the Johnson-Windman-Strauss lemma. I mean, you can just embed one metric space in a lower dimensional metric space with distortion. And then there's a
you didn't know that.
And you don't need to know anything. You just need to know the dimension and the amount of distortion to allow it. In fact, the dimension that you require depends much more on the error. It's only like logarithmic in the original dimension, but then over the error squared. So you don't need to know much about the metric space. The question is if that exists for the directed.
I don't know. I didn't know about this story. What I was thinking about was basically just kind of directly comes from the point of view of using bimodules when you have a Morita equivalence. And then from the fact that, the sort of, when you look at the layers of a neural network, you're kind of composing these matrices. So you have like bimodules basically. So you can, and the input and the output is your category, but then you have all these intermediate steps that you can be composing. But yeah, thank you. I'm going to look into that. Yeah.
I think my question was just half answered, but I was, so I'm kind of thinking of this P of L as being like the category of modules for L.
Yeah, absolutely. It is the category of modules. I should say that, yeah.
With like tropical numbers instead of abelian groups or something like this, so kind of like a ring and its modules. So my question was about bimodules, exactly.
Yeah.
So it sounds like you have some pretty direct understanding, because that's normally, as I learned from you, that's the normal way to treat Morita equivalence.
Yeah.
So it sounds like you have some literal interpretation of bimodules in terms of layers or something.
Well, yeah, no, I mean, it's not clear to me exactly how, but this is what I'm trying to understand, yeah. Yeah, I mean, an obvious bimodule, I don't know if this is the right one or not, but kind of one that comes to mind immediately is that instead of having continuation in the same language, you may want to consider basically a text and its translation, and then consider the continuation in the other language. So you have the one text in one language and the continuation in another language. And this would be a bimodule between languages, basically. But actually, you're very right, I should point this out, that all this duality about ideals that I said before and so on, I mean, when you do, this only works basically in the commutative world, in the non-commutative world, which we live in reality. You have to consider modules, okay? Ideals are modules. Modules are just a little bit more general. And presheaves for algebras are precisely modules, actually, or representations. So when we're talking about presheaves, we're talking about modules or representations, basically, the space of representations.
Because the other ones are co-modules.
Right, the other ones are co-modules, yeah, that's right, yeah. Left and right modules, if you want, yeah.
Do you think about some examples? Maybe, for example, instead of languages, people also consider graphs. And there's node to vec, which you can do the same embeddings. So, and if you take some simple graph, just square, for example, then do you have expectations? What should it be?
Yeah, or some, I haven't tried, no, I haven't thought about it, or some artificial language, like Mike has been pointing out to me.
Language can be...
Or an automaton.
Yeah,
for example.
Yeah, or from groups, for example, we have the geodetic language of groups.
No, but it's interesting, but I haven't done it. Yeah, it would be interesting to do, definitely. Some sort of more small scale thing. Yeah.
Okay, well, let's thank Yiannis.